everyone. I am Thikra Dawood, postdoctoral researcher in the School of Construction Management at Purdue University. On behalf of our research team, Dr. Emad Elwakil, Hector Mayol Novoa, and José Gárate, and myself, I'll be presenting our research paper, failure prediction of PVC transmission pipes using data-driven modeling. Our agenda for today starts with the introduction related to the water distribution networks, followed by the literature review. Then I'll explain in detail the methodology of our research, followed by the model development. And in the end, I will wrap it up with the prospective future work. In the United States, potable water is delivered through 1 million miles of pipes to the consumers over the country. Polyvinyl chloride pipes are currently used in 80% of the water distribution networks in North America. This is because of their lightweight, low cost, and ease of jointing. However, due to the excessive operating conditions of these pipes and through-wall residual stress, cracks will initiate, causing those pipes to be break, and also to have failure in the future. The consequences of this also will even worsen due to the internal water pressure. However, there are also different prediction models to be researched to solve this problem. PVC pipes are known to be fairly new pipes. However, limited failure data are available about those pipes. The main objectives of our research is to model pipeline deterioration using data-driven modeling, also to handle the scarcity of data, and third, to quantify the water main failure rate in the future. An extensive literature review revealed that there are several failure prediction models in the literature. Such models could be found in Sattar et al. 2019. Sattar developed a failure prediction model and also a management system using extreme learning machine. Winkler et al. 2018 estimated the deterioration rate and failure mechanisms through boosted decision tree. Malinowska 2017 predicted the water main failure through the fusion of the GIS and fuzzy inference system. Kutuliwska 2016 predicted the pipe failure rate using the support vector machine and artificial neural network. Other models were found also in the literature related to the risk assessment, such as Petrushka, Urbanik, and Stuzewski 2019.
Sorry for interrupting, guys. Do you see the presentation slides?
What?
No, we don't see it, Dr. Elwakil.
So, okay.
We just see the folder.
Yeah, guys, if you, okay.
So I see only the
Oh,
Oh,
Do
okay.
you see it now?
Now it's okay. Yeah.
Yes, yes.
Okay.
Okay.
We see it
Thank
now.
you.
Thanks.
Okay, guys.
Thank you.
Okay, so other models also were developed related to the risk assessment, such as Fayaz et al. 2018, through the integrated risk model using hierarchical fuzzy logic and Kalman filter. Also, Lai and Yao 2016 developed a risk index system through AHP and fuzzy logic. Christodoulou et al. 2010 developed a proactive risk model using a survival analysis and artificial neural network. However, none of these previous models was able to predict the failure of water main, especially using the hydraulic pressure and the flow rate in these pipes. Therefore, this research was able to develop a methodology in 5 stages, starting with the data collection and the water distribution networks of El Pedregal city in Peru. The pressure, the internal pressure of the pipe and the flow rate were taken as crucial factors in this study. In the second stage, the data preparation stage, we were able to select a predictor variable and a response variable. The predictor variable was the hydraulic pressure, and the response variable is the failure rate of these pipes. This is followed by generating and writing code and script in MATLAB 2019. In the third stage, the simulation and regression analysis were conducted, and then the results were analyzed, producing different polynomial functions, and then different regression models were also created. In the fourth stage, we were able to test these models through statistical tests, which included R-square and the root mean square error, in order to underscore the goodness of fit for these models and select the best model according to the highest R-square and the lowest root mean square error. The best model was validated in the fifth stage using residual analysis and different statistical metrics, such as the mean absolute error. This slide shows the study area in our research, which was the city of El Pedregal in Arequipa region in Peru. This city was selected due to its booming economy. Also, this city was considered as one of the congested area in the region. Therefore, there was an increased demand on the water distribution networks in this region and in the city of El Pedregal in specific. These are the results from our model, which included 3 models: the linear model, which is first degree order. The second one is the quadratic, which is a second degree order. And the cubic, the third one, is the third degree order. In all of these models, X represented the hydraulic pressure and Y is the pipe failure rate. This slide shows the 3 models. on the left, the schematic presentations of these models. The top one is the linear, the middle is the quadratic, and the third one is the cubic. We were able to compare the results of these three models through the table on the right side. Here we can see that the cubic was selected as the best model as it had the highest R square and the lowest root mean square error. And that best model was validated through different residual analysis schemes and also through statistical mean absolute error. As we can see here, the schematic drawings of these validations for the cubic model and the low error that it shows. For prospective future work, different models could be developed using remote sensing technologies for the detection and localization of the leakages in water distribution networks. Also, integrated condition assessment model could be developed using physical, environmental, and operational factors. And the third one, another model could be developed using sustainable management framework to identify the earthquake, the floods, and landslides. These factors are natural disaster factors that could lead to the failure of the pipes. Thank you for listening. And now let's take some questions.
Thank you, Dr. Dawood. I appreciate if there are some questions. If anybody want to ask, please go ahead and ask.
What?
Questions.
Okay.
Anybody?
May I ask, yeah?
Go ahead.
I have a question.
Go ahead.
I have a question.
Yeah.
My question is, to
Como é
begin,
que eu
you
faço para
said,
ver todos os carinhas aqui?
do you hear? To begin, you said that you have pressure and flow.
Yes.
Do you hear me?
Yes.
No, moment. To begin, you said that you have pressure and flow,
Yes.
but you analyzed only pressure. Why not flow? Do you understand?
Yeah. Yes. Yes. Actually, the flow rate was included also in the main model. But when we took the pressure as the maximum pressure and the internal pressure, the flow rate was included internally with the pressure. So it was taken into consideration in the simulation.
Okay.
It's not the pressure,
Okay.
but then the pressure was the main item.
Okay.
Yeah.
The next question is, you mentioned that there were investigations, researches about fuzzy and Kalman filter from other authors.
Yes.
Have you also proved, or have you tried also to do with fuzzy and Kalman, or not?
Yes, actually, there was another paper, research paper that we produced as a team, and it was submitted to the Journal of Engineering Failure Analysis, and it was accepted also regarding the fuzzy logic and the fuzzy inference system modeling. So it was covering that part area of the research.
Okay.
Yes.
And my last question is, I have seen 3 diagrams with linear model, quadratic, and cubic. Can you
Yes.
show once more? Can you show it?
Yes.
So there are the
Or
equations.
the schematic, yes.
And you know, I expected that I will see here a cubic, quadratic curve and a cubic curve, but all curves are linear. That means I don't understand what the points is clear. The points are experiments. The points.
Yes, yes.
And the line, what is the line?
This is a regression line. The regression line actually, because the data was were not so much. I mean, as data points, were not able to show the cubic and the quadratic. It shows a little. If you concentrate, there is a little curvature, but because of the little amount of data points, we were not able to show the curvatures.
Okay, okay,
Yes.
thank you.